Okay, let's go ahead and get started. So today we are going to continue with our discussion of the classic tests of general relativity, which, as we saw before, are really, in a sense at least, tests of the Schwarzschild solution of general relativity. So as you are probably tired of hearing at this point, the Schwarzschild solution of general relativity is the solution that describes the metric in the presence of a static, spherically symmetric object. The Schwarzschild radius, capital R here, is the length scale, which sets the typical scale of curvatures in the Schwarzschild geometry. And is equal to twice Newton's constant times the mass of the object. And last time we spent some time studying the geodesic equation in the Schwarzschild geometry. And we saw that the geodesic equation for time-like geodesics, which are the geodesics which are the paths of motion for normal massive objects such as satellites, rocket ships, planets, and so forth, those geodesics are governed by the dynamics of an equation which is the equation of motion of a one-dimensional particle. So just as in Newtonian mechanics, when we study the Kepler problem for determining the orbits of the planets, for example, that reduced down to a one-dimensional equation of motion where we had an effective potential with an angular momentum barrier, and by studying the solutions of that motion, we saw that the orbits are conic sections. Last time we saw that in the presence of general relativity, this story is very similar, the exception being that the effective potential had an additional term that went like 1 over r cubed and was suppressed by the speed of light squared. So it was a very small correction, but it was a correction with measurable effects. And it led to all sorts of interesting effects, including, for example, the precession of the perihelion of Mercury, which is the statement that in general relativity, the orbits of the planets are no longer exactly conic sections, they're no longer exactly ellipses, but rather they precess in a complicated way, and a computable way, which we derived last time. So, what we're going to do today is continue our study of the geodesic motion of objects in general relativity. But what I would like to focus on today are not time-like geodesics describing the motion of planets, for example, but instead I would like to discuss the motion of null geodesics. So what is a null geodesic? A null geodesic is a geodesic that moves in a light-like rather than a time-like direction. And so the null geodesics will describe the motion of light in the Schwarzschild geometry. So we wish to study the motion of light in the solar system where we take into account the fact that space-time has curvature. Now, sometimes people say, loosely speaking, that light has mass. So there's a sense in which this is true. As you learned in your electromagnetism classes, light has energy. And in special relativity, energy is equal to mass times the speed of light squared, so light has mass. But in order to make that precise, we really needed to use the notion of general relativity, where the precise way that one studies how the trajectories of light are affected by gravitational objects is by studying null geodesics in the curved spacetime of that object. So we wish to study, for example, the deflection of light rays due to the curvature of spacetime This is a rather famous effect and one of the most well-studied effects of general relativity, which is known as gravitational lensing. So today we will, by studying the motion of null geodesics in the Schwarzschild geometry, begin a study of gravitational lensing, and we'll derive, for example, the famous effect that was observed by Eddington in the early days of the 20th century, as well as other effects that are studied by astronomers today. Before I begin our discussion of gravitational lensing, let me pause here and see if there are any questions. So the story that we are going to be developing will follow very closely the story that we developed last class for time-like geodesics. So just as for a time-like geodesic, the symmetries of the Schrödinger space, of the Schwarzschild spacetime, lead to conserved quantities. So as before, our null geodesic will be parameterized by four functions x mu of lambda, where again lambda will be taken to be an affine parameter that labels points on the null geodesic. And again, as before, we will consider only today those geodesics which are confined to the plane where theta is equal to 0. So this is the equatorial plane. Of course, we have a full rotational symmetry, so we could always just choose our coordinate theta so that our geodesic lies in the theta equals 0 plane if we liked. So this is merely a matter of convenience rather than any restriction on the generality of the geodesics that I will be writing down. So, as before, the killing vectors which describe the symmetries of the Schwarzschild geometry will lead to conserved quantities. The argument is identical to the argument that I gave last time. For example, there is a conserved energy, meaning that associated with this geodesic there is a quantity E, which is independent of lambda, which is proportional to T dot, and there's a quantity L, which is the angular momentum of the geodesic, which is proportional to phi dot. And these are constructed by contracting the killing vector with the tangent vector of this geodesic. And for an affine parameter, then these will be independent of lambda. The difference with the story we learned last time for time-like geodesics comes when we use the fact that because the geodesic is null, ds squared is equal to 0, or ds by d lambda squared will be set equal to 0 rather than equal to minus 1. That's what we mean when we say we have a null geodesic. So if we plug that in to the Schwarzschild metric, that says that 0 is equal to minus 1 minus big R over little r T dot squared plus 1 minus big R over little r inverse times R dot squared plus R squared phi dot squared. So here I'm just going ahead and plugging in the equation for ds by d lambda squared into the expression for the Schwarzschild metric. Is that clear? This is exactly what we did last time. And then using the expressions for T dot and phi dot that we can derive from these conserved quantities, we see that this can be written as a first order equation for R and R dot, which I will write down here, and it involves R dot, the angular momentum L, and the energy E. And this is exactly the same as the equation that we wrote down last time for the time-like geodesics, except it's even simpler. There's a 0 on the left-hand side instead of a 1. That's the only difference. But it will lead to rather different physics when we study null geodesics than it did for time-like geodesics. So again, we could rewrite this so that it looks like the equation of motion of a one-dimensional system in an effective potential. So I will call the effective potential V effective, and you can just go ahead and plug and manipulate this equation. You multiply it by 1 minus big R over little r. You divide by 2, move the e to the other side of the equation, and what do you get? You get that V effective is equal to L squared over 2R squared minus, L squared over R squared divided by 2 times 1 minus big R over little r, which is L squared over 2R squared minus big R over L squared times 2R cubed. Is that clear? So if we wish to study the motion of null geodesics in the Schwarzschild geometry, we now just need to study these particular equations of motion. And in fact, this effective potential should look quite familiar to you. It's the same effective potential we looked at last class for time-like geodesics, except it's missing one term. Well, it's missing two terms. It's missing a constant 1/2 term, which we threw away anyway, because constants don't affect the motion of a one-dimensional system. But it's also missing the term which looked like 1 over r in the equation for a time-like geodesic. What was that 1 over r term? That was the standard 1 over r squared force law in Newtonian gravity. So the equation which governs the dynamics of light rays in a curved spacetime is exactly the same as the one that governs time-like geodesics, except the difference being that there's no 1 over r squared force law. We still have this angular momentum barrier, and we also have the new term which arose because we're studying general relativity. This was the term that led, for example, to the precession of orbits in the case of the planetary orbits, as we discussed last time. Okay. There's a hell of a lot of physics that we can extract from this formula. And much of this class today will be devoted to understanding that physics. Yes, question?
How can light have a
Well, we will see in just a minute that this angular barrier term is precisely what in Minkowski space says that light travels in a straight line. So let me just say that a little more precisely. If you studied the motion of light rays in Minkowski space, then you would know that light travels on a straight line. And in Cartesian coordinates, that would tell you that there's no potential term that will change the dynamics of the light ray. But we're not using Cartesian coordinates. We're using the analog of polar coordinates. So if you studied the motion of light in Minkowski space in polar coordinates, you would find that in terms of the r term, there's effectively some sort of centrifugal term, which will tell you that r dot is not a constant, but rather depends on r. And that's precisely what this term is. This is precisely that first term. You never study the motion of light rays in classical mechanics because usually you don't consider special relativity in classical mechanics. But you certainly could have. And if you did, you would have found precisely this term if you studied the motion of light rays in flat Minkowski space in polar coordinates. We'll see that very explicitly in a few minutes. So, before solving this equation, we can, of course, solve this equation, and that's what we're going to do later this class. But before we do so, let me just draw this effective potential for you. So, at large r, it goes to 0 like 1 over r squared rather than 1 over r as we had for the case of a time-like geodesic. And for small r, the effective potential goes to minus infinity, like 1 over r cubed. So we see that there is a local maximum at a radius that I will call r crit. And how do you find r crit? You just set v prime equals to 0 and solve for r, and you find that it's equal to 3/2 times the Schwarzschild radius. So what does this mean? This means that there is no stable circular orbit for light. Okay, that's not such a surprising thing. But there is an unstable circular orbit for light at a radius which is equal to 3/2 times the Schwarzschild radius. And moreover, this light ray will either go off to infinity or it will fall into the center of the geometry. So just looking at this effective potential, you can see that light will either go to infinity or go to r equals 0. And in fact, there's something else that you can actually extract from this potential, which is the following. So off at r goes to infinity, v is going to 0. But at small values of r, this effective potential is actually less than 0. So you could ask, where does this potential cross v equals 0? And that's easy enough to determine. You just stare at this potential. Where is that equal to 0? That is equal to 0 when r is equal to the Schwarzschild radius. So if r is less than the Schwarzschild radius, v is less than 0. And so from the point of view of this one-dimensional mechanics system, if you start at r less than the Schwarzschild radius, then you could never get out to r equals infinity. And in fact, this is a signature of the fact that the Schwarzschild radius is a so-called event horizon, behind which, from which light cannot escape. And this is something that we will return to next class when we begin our discussion of black holes. So this is the region which is so-called behind the event horizon. Now, I should emphasize that we are using coordinates which broke down at the Schwarzschild radius. The metric became singular at the Schwarzschild radius, so we really shouldn't trust anything that we're saying for values of r less than the Schwarzschild radius. I'm merely pointing this out to you to show you that something interesting is happening to these equations there. But in order to understand the physics, we'll have to wait till next time when we start constructing coordinate systems that allow us to smoothly study physics as we go into the horizon. Yes, question?
But at 3/2 the Schwarzschild radius,
Yes.
light is doomed to go into this Schwarzschild.
Not necessarily. Because, for example, because remember that we have in this equation not only a potential energy v effective, but a kinetic energy. So if you're just studying the dynamics of a particle in this potential, in principle you could start with sufficient initial velocity to climb back out of the barrier. And although I haven't proven this to you yet, if you start at r less than the Schwarzschild radius, you can never have enough initial energy to climb, initial kinetic energy to climb over that potential barrier. So that's something that you can't really see in this picture because I'm using coordinates that went bad at r equals the Schwarzschild radius. So I'm going to defer any discussion of that until next class when we construct coordinates which allow us to smoothly study physics as we cross the event horizon. Instead, today I would like to focus on normal physics, where the radius is much larger than the Schwarzschild radius. And as before, what I will do is treat the 1 over r cubed term in the effective potential as a small perturbation. So, what is our equation of motion? Our equation of motion is 1/2 r dot squared plus v effective is equal to a constant, which I will just call E hat, where v effective was the sum of two terms, the first of which was the usual angular momentum barrier term, and the second of which was the relativistic correction term. Any questions so far? We're now going to dive into a little bit of algebra. The algebra won't be quite as bad as it was last class. In fact, it'll be the identical algebra that we went through last class. So, in order to write this equation of motion in a more manageable form, as just last time, I am going to make a change of variables, where instead of studying r of lambda, I'm going to study r of phi, and instead of studying r, I'm going to study the quantity u, which was proportional to 1 over r, with that same constant of proportionality out front, just to make our lives easier. And so prime will denote d by d phi. And so then it's the same set of manipulations I went through last time to write down the differential equation in terms of u instead of in terms of r. And what do you get? Well, you get exactly the same thing you had last time, except with a couple terms missing. So this is the exact same set of manipulations I did last time. I don't want to bore you by going through it all again. Last time we said we took r to depend on phi instead of on lambda, and we took u to go like 1 over r, and we found some first-order differential equation for u. And this is the same first-order differential equation, except that the terms that weren't there in v effective are now not here in our equation. And as we did last time, I would again like to take the derivative of this with respect to phi in order to turn this into a nice equation that we'll be able to solve easily. And so if we take the derivative of this equation for u with respect to phi, and then we divide by 2u prime, you get the equation u double prime plus u is equal to 3/4 r squared over L squared times u squared. So this is exactly the same equation that we had last time for the motion of time-like geodesics. The only difference being that last time, on the right-hand side of this equation, we had 1 plus 3/4 r squared over L squared times u squared. So the only difference with the time-like case is that there is no constant term which appears in this equation of motion. But it can still be regarded as a simple harmonic oscillator with a driving term, at least in the approximation where we treat the quantity appearing on the right-hand side, which is the new relativistic correction, as a small perturbation. So that is what I am now going to do. Before I do so, let me just pause and see if there are any questions. Okay, if there are no questions, then it's perfectly straightforward to go ahead and study the physics of the solutions to this equation. So what we will do is we will expand in a perturbation series so that u is u0 plus u1 plus higher order terms, where u0 is a solution of the equation of motion where we just neglect the general relativity correction. So it's a solution of u prime plus u equals to 0. Well, that's an easy equation. Even I can solve that equation. That's the equation of motion of a simple harmonic oscillator. So that u naught will be a linear combination of sines and cosines. And I will just choose my constants of integration so that u naught is c times cosine phi, where c is some constant of integration. So I could always just shift phi in order to make u look like a cosine rather than a linear combination of sines and cosines. So before understanding the relativistic corrections to this trajectory, it's worth understanding this trajectory itself. So what is this trajectory? This is the trajectory that is supposed to describe the motion of light without the general relativity correction. And light travels on straight lines in flat Minkowski space. So this had better be the equation for light which travels on a straight line. So let's see why that's the case. So let's go ahead and compare this. Let's go ahead and write out r. So r was 2l squared over r times u, which in these coordinates is 2l squared over r times c cosine phi for this solution. Or we could simplify this by writing this just as b over cosine phi, where I've defined the constant b to be 2l squared over rc. C here is not the speed of light, it's just some constant of integration. I probably shouldn't have called it c, but it's too late now. Okay, let's stare at that equation for a second. In flat Minkowski space, the quantity r cosine phi has a name. It's the x-coordinate, right? In Cartesian coordinates, x is r cosine phi, y is r sine phi. So this is just the equation for a trajectory in flat Minkowski space with x equals constant. So, and that, of course, is a straight line. And it's a straight vertical line in the standard Cartesian coordinates. So in these coordinates, the center r equals 0 is at x equals 0. And the trajectory is at r equals b. So, for example, if you are studying the motion of light rays moving near the sun, then the sun would be at r equals 0. And the parameter b that I defined here has a simple physical interpretation. It has dimensions of length, and it's the distance of closest approach that this light ray gets to the sun. I don't know if that was a complete sentence. B is the closest distance that this light ray is to the sun. And in particle physics and gravitational physics, we usually give a name to the distance of closest approach. We usually call it the impact parameter. So we see that without the general relativity correction, we're just studying flat Minkowski space, and light rays, as expected, travel on straight lines in flat Minkowski space. So without the GR correction, this describes light moving on a straight line. And the only subtlety is that I'm parametrizing this straight line in polar coordinates rather than in flat coordinates. I should make one more comment about the parameterization of a straight line in polar coordinates. which is that r here starts out at infinity when phi is equal to minus pi over 2. So phi here is the angular coordinate. Let's draw this out a little more explicitly. So if this is the sun, then phi here is the angular coordinate, and r is the radial coordinate. So our equation of motion, r equals b over cosine phi, describes a light ray that is at r equals infinity when phi is equal to minus pi over 2. It's at its point of closest approach when phi is equal to 0. And r is going off to infinity again when r goes to plus pi over 2. So for this light ray, phi is running from minus pi over 2 to pi over 2. And r is starting at infinity, going down to some constant value, and going up to infinity again. Any questions on that? Okay. So let's go ahead and compute the first perturbative correction. So in perturbation theory, we are expanding u is u naught plus u1 plus dot dot dot, and u is trying to solve the differential equation u double prime plus u is equal to 3/4 r squared over L squared times u squared. So u naught was the solution with the quantity on the right-hand side neglected completely. And the first correction, u1, will be the solution of the equation u1 double prime plus u1 is now equal to the right-hand side, but with the right-hand side evaluated only including the u naught term, which will be the largest contribution to u. So 3/4 r squared over L squared times u naught squared. Which, if we plug in our expression for u naught given above, so u naught, let's go look at what it was above. U naught was c cosine phi, or 2L squared over RB times cosine phi. So if we go ahead and plug this in, this is 3 times L squared over B squared cosine phi squared. And this is the equation for a simple harmonic oscillator with a driving force. And again, we can solve this by using the method of Green's functions. So the solution to this equation says that u1 is the integral d phi prime of the source term, cosine squared of phi prime, times the Green's function for the simple harmonic oscillator, which is sine of phi minus phi prime. And there's that coefficient out front, 3L squared over B squared. And this is integrated from minus pi over 2, which is the start of the trajectory off at r goes to infinity, up to phi. Now again, we can go ahead and look in our favorite table of integrals, or just think a little bit and do the integral ourselves. That actually is the easiest thing to do. That's the secret. I won't bother going through the details. You all can do integrals by yourselves. I'll just tell you what the answer is. The answer is some simple trigonometric functions. So it's 1 plus sine squared of phi plus 2 sine phi. So what does that mean? That means that u, which was u naught plus u1 plus higher order corrections, So what was U naught? U naught was 2L squared over RB times cosine phi. And the U1 correction is given right here. So that is plus R over 2B times 1 plus sine squared phi plus 2 sine phi. And then plus higher order terms. Now, we should emphasize that we want to regard this first correction term as a small correction to the original U naught. And you can see here that it's all multiplied by the parameter R over 2B. What is R over 2B? That is the ratio of the Schwarzschild radius to the impact parameter. So if the point of closest approach of this light ray is very large compared to the Schwarzschild radius, this will indeed be a small parameter. And the approximation that we're talking about will be a reliable approximation. For example, if you're looking at light rays which are passing close to the surface of the sun, this will be the ratio of the radius of the sun, the physical radius of the sun, to the Schwarzschild radius of the sun, which indeed is a very, very small parameter. I don't know what it is exactly. It's probably 10 to the minus 4, 10 to the minus 5, something like that. All of the higher order terms will be suppressed by further powers of R over B. Yes, question?
In the integral for the Green's function, where are we working from minus level 2 to pi and not to minus level 2 to pi over 2?
If you wanted to understand, so because we're using the method of Green's function, that's what you do.
Come from Green's function? Phi minus phi prime?
Yeah, there's a phi minus phi prime in the Green's function. But if you want U of phi, you only want to take into account the driving forces which happen earlier, right? Is that clear? I mean, this is the equation of motion for a simple harmonic oscillator with a driving term. You want U of phi to be responding to the driving term which happens for values of phi prime less than phi. Otherwise, your harmonic oscillator is reacting to things that happen in the future. Okay. Is that clear? Yeah. I encourage you to just go ahead and plug this in, and you'll see that this is the right solution to the differential equation. So you could then go ahead and draw this on the R phi plane or on the XY plane. And what does it look like? Well, I'll tell you what it looks like. So, at large values of the radius, light still has to travel on approximately a straight line. So that you know that at large values of radius, this will look like a straight line. But at values of the radius which are not very large, it will not look like a straight line. So what does it look like? It looks like the light is going to be deflected by the massive object. So if you just graphed U as a function of phi, or graphed R as a function of phi, what would you get? Well, here, let me scroll down to the next page so that we have plenty of room. Well, the initial trajectory was a straight line where, say, we had the origin, which was the sun, over here. And then the initial trajectory just continued on a straight line. So we know that at late times, our actual trajectory, as we've found above, where U is equal to 2L squared over RB times cosine phi plus R over 2B times 1 plus sine squared phi plus 2 sine phi. We know that that is going to look like a straight line at large values of R, just because light travels on straight lines very far from massive objects. But it'll be curved in some way. And the shape of that curvature is determined by that function U of phi. So you could draw it out explicitly if you like, but that is what I've sketched here. And so the end result is that the light ray will be deflected by the presence of the massive object by an amount which is the angle delta phi, which you can compute just by looking at this expression for u that I have written down here. So, what is the angle delta phi? Well, let's just go ahead and compute this. So, the angle delta phi is determined by finding at what values r goes to infinity, which is to say, at what values u, which is 1 over r, will go to 0. So we need to ask, for what values of phi does u go to 0? And those values should be very close to pi over 2 and minus pi over 2, but not exactly equal to pi over 2 and minus pi over 2. So you can just look at what u looks like near pi over 2 and minus pi over 2. So if you let phi be very close to minus pi over 2, then u goes like 2L squared over RB times delta phi if phi is equal to minus pi over 2 plus delta phi. That's just because when phi is equal to minus pi over 2, where r is very large, and we haven't even gotten anywhere near our massive object yet. And so we just have that cosine phi term, and cosine phi has a first order 0 at phi equals minus pi over 2. So that's just the usual statement that this trajectory will begin at phi equals to minus pi over 2. But if you now look at phi being close to plus pi over 2, then we have delta phi again coming from the cosine phi, but we also have a correction coming from this 1 plus sine squared phi plus 2 sine phi term, which the first order in delta phi is equal to 4. So that's plus 2r over b. And that's for phi equals approximately equal to pi over 2 plus delta phi. So what do we see? We see that in the presence of a massive object, light is deflected by an angle delta phi, which is equal to 2r over b, or 4gm over b. And that is in the approximation where the object is close to spherically symmetric and static, and the light is not passing too close to the object. And the angle of deflection depends linearly on the mass of the object and is inversely proportional to the distance of closest approach of the light to the object. And this effect is known as gravitational lensing. And it is one of the best observed effects of general relativity. So, for example, if you just go ahead and plug in some numbers, you plug in the mass of the sun and the radius of the sun, this means that for light rays passing near the sun, delta phi is of order a few seconds of arc. Now, when would this be observable? Let's imagine that we have a star which is very far away. Its light rays usually travel on straight lines, but if you happen to be able to observe the light rays as they pass very close to the sun, then those light rays would be deflected, meaning that the apparent position of those stars on the sky would move by a few arcseconds. And, of course, it's generally very hard to observe stars which are very close to the sun in terms of their position on the sky, but, in fact, it can be observed during a total eclipse. And this was the first experimental verification of general relativity, famously by Eddington in the second decade of the 20th century. Now, there's actually been some controversy and discussion as to whether or not Eddington might have fudged his results a little bit, and whether or not he actually observed the effect to the degree of precision that he claimed. I'm not completely familiar with all of the detail, but I do know that even if you don't want to believe Eddington's result, this has been observed in much greater accuracy many, many times since then. And in particular, we most commonly hear about it nowadays not in the context of total eclipses, but rather in the context of astrophysics. And it is very commonly observed in astrophysics. So what is the typical setting? Well, the typical setting is that you would have some massive object sitting here, something like a galaxy, and then you would have, so we're sitting over here, so that's our eye. Sorry, that's not a very good drawing of an eye. Looks more like a Freemason symbol, but it's an eye. And here we have some very distant, very bright object, usually a quasar. And the light from this quasar, rather than traveling to us directly where it would be obscured by the galaxy, instead will be bent a little bit so that we will in fact see two apparent images of the quasar. So from our point of view, it will look like we have some sort of doubled image of the quasar with a angular separation between the two of them, which is related to the mass of the galaxy as well as the distance between us and the quasar. And in fact, this is an extremely useful tool in astrophysics. One of the reasons that it's useful is that although I have derived for you the expression for gravitational lensing for a spherically symmetric object, it is reasonably straightforward to, using a similar approximation scheme, derive the equation for lensing for other more complicated sets of objects. And in fact, we can use lensing to determine the mass distribution of the galaxy. So we saw that for a point mass, we have 4gm over b being the angular deflection. But if you have some more complicated configuration of point masses, you can integrate over all of that, and you can get some, if you have some very nice, very precise lensing image, then you can extract from that the mass distribution of the galaxy that you're studying. And this is a very clever and very effective way of understanding the mass distribution of certain objects. And one of the nice things about it is that you don't never have to actually observe the matter in the galaxy. So, for example, if you have matter which does not emit light, maybe some dark sort of matter of some sort, then this would be a very effective tool for understanding the location and the amount of that dark matter, even without being able to observe it directly. So, if you have a perfect setup where your eye, the galaxy, and the quasar all lie on a line, In fact, you will not just see a double image, you'll see an entire ring of images that you would obtain by rotating this image around the axis between our eye, the galaxy, and the quasar. So in a perfectly spherically symmetric setup, you would have what is known as an Einstein ring, which would be a perfect circular image on the sky coming from this quasar. If you have something that's slightly off-kilter, you would get a complicated series of arcs of various distributions of intensity. And so, by studying in detail this gravitational lensing, you can actually learn quite a bit about what's going on. Indeed, there are, in fact, two different kinds of lensings that people talk about in astrophysics. So far, we've talked about what is known as macrolensing, which is where you can distinguish the light from the two different sources, say from two different images, or distinguish the light as having the shape of a ring. But there's also what's known as microlensing. That is where you can't even observationally distinguish these two images, but nevertheless you can tell that lensing is occurring because the image is going to get a little bit brighter. So, for example, if you have some galaxy which is moving across your field of view, and there's a quasar which is being obscured by that galaxy, then in fact you would expect that the brightness of the quasar will double as it is obscured by this galaxy, because you now have the total light from two images rather than one. So even if you don't have the resolving power to distinguish those two images, you'll still have twice the amount of light. And so this is in fact another way that astronomers try and determine how many galaxies there are out there and how much mass they have, just by studying how the brightness will fluctuate in time. And indeed, there have been many, many lensing events which have been observed, both macrolensing and microlensing. And this is one of astronomers' favorite ways of trying to find out how much mass is out there in the universe and what its structure is. Question?
Why does it double?
It will double because you have two images. And
But if it's symmetric,
oh, yeah. No. I'm assuming that it's not quite. Yes. So when I double, I'm being a little sloppy. So of course, it will depend. How much magnification you get will depend on exactly how symmetric your lensing event is. If the galaxy happens to pass exactly through the line between our eye and the quasar, you would get a whole ring. And so you would have to do a little computation where you integrate over the ring to see how much enhancement you get in the brightness. So yes, it will depend in more detail on the structure of the lensing event. Yeah, so when I say double, I mean I'm being a little sloppy there. Good question. Any other questions? Okay, so gravitational lensing is the second of the so-called three classic tests of general relativity. And in the last 20 minutes or so, I would like to describe the third and, in some sense, the simplest experimental test of general relativity, which also involves null geodesics traveling through a curved spacetime, but it's a much simpler effect, and it only involves the redshift of the wavelength of light as it moves through a curved spacetime. Before I continue on to the discussion of gravitational redshift, is there any question or concern about gravitational lensing? Okay. Gravitational redshift is actually rather simple, and there aren't even too many equations that we need to write down in order to understand the physics and the origin of gravitational redshift. So I would like you to start by imagining that we have two observers which are sitting at different radii, so different vertical positions in the Schwarzschild geometry. If you like, it would be a good idea to imagine these two different observers to be sitting, say, in the basement and the top floor of a physics department on the Earth. So this would be the Earth, whose metric is described to a great degree of accuracy by the Schwarzschild geometry. And I have drawn, not to scale, the height of a physics department here, whose basement is R1 and whose top floor is R2. And I want to remind you that the Schwarzschild metric includes a term like 1 minus big R over little r times dt squared plus a bunch of other stuff. But I wish to consider observers who are just sitting at fixed r and fixed angular position, so those other terms won't be relevant. So for one of these observers, so let's say for an observer at a constant radial position, so let's say at position Ri, so R equals to Ri, where I is equal to 1 or 2, then you could ask how much proper time elapses for that observer as measured by a clock which this observer is carrying with them. And you could ask how much proper time elapses per coordinate time t. So we label events in the Schwarzschild geometry using the coordinate time t, which, because of this term in the metric, is not identical to the proper time that has elapsed according to an observer who is sitting at fixed radius. And in particular, for an observer at fixed position Ri, the proper time, which I will call tau I, elapsed per coordinate time t is given by tau I is proportional to t, but with a constant of proportionality that involves the factor 1 minus the Schwarzschild radius over r that appears in the metric. All I have done here is I've used the fact that the proper time elapsed is the square root of minus ds squared integrated along the observer's world line. So if you have a coordinate time t, then the proper time which is elapsed will be related to that coordinate time interval t by an amount that depends on where you're sitting. So for example, t1 is going to be different from t2. So you could then imagine that these physicists sitting on the bottom and top floors of this physics department perform the following experiment. So let's imagine that the observer at R1 sends a signal to R2 and sends this signal once per proper time lambda 1. So after a proper time lambda 1 elapses according to my clock sitting here at R1, I will click on my flashlight and then click it off again. So I'll send a signal once per proper time lambda 1. And that will occur once per coordinate time t, where t is related to lambda 1 by this factor 1 minus big R over little r1 to the 1/2 power. And then you can ask, what will be the proper time elapsed between observations of this signal by the observer at R2. So this signal will be received by the R2 observer once per proper time lambda 2, where lambda 2 is related to lambda 1 by the factor which is given by the ratio of these two factors that appeared up here. So it's 1 minus big R over R2 divided by 1 minus big R over R1, all to the 1/2 factor. And this will be larger than lambda 1 if R2 is bigger than R1. So if I send a signal up to my friend on the top floor of the physics department once per second, then my friend on the top floor will receive these signals once per 1.1 second. Okay, it would have to be a very tall building in order for this to be true. But he will receive these signals at an interval which is slightly longer than 1 second. Okay, now let me imagine sending a slightly different sort of signal. Let me imagine sending light with a given proper wavelength. What is the wavelength? The wavelength is the time elapsed between peaks of the electromagnetic wave that I'm sending. And so, in fact, the exact same thing will be true if you think about sending a light ray. You could think about a light ray as a bunch of little signals spaced by proper time lambda 1, where lambda is the wavelength of the light. So if R1 sends light with wavelength lambda 1, the wavelength, okay, that's not a very legible word. The wavelength observed by the observer at R2 will be different from the wavelength of the light which is sent. And they will be related by the factor, which is 1 minus R over R2 times 1 over R minus R1 to the 1/2 power. And this is also the ratio of the frequencies. So the frequency is 1 over the wavelength. So this will be the ratio of the frequency, omega 1 over omega 2. And this is known as gravitational redshift. And the basic idea is that light, which comes from deep in a gravitational potential, will be redshifted. If I, in the basement, am sending blue light to my friend on the top floor, it will be slightly redder, perhaps only a tiny, tiny, tiny bit redder, by the time it arrives to my friend on the top floor. And in fact, this was the third classic test of general relativity proposed by Einstein, which was in fact observed in the 50s by Pound and Rebka. So this was first observed by Pound and Rebka. I believe it was in the 50s. I'm not actually sure. But since then, it has become, in fact, a rather commonplace effect, and perhaps the most widely used effect of general relativity. Every time you use a GPS receiver, in fact, that GPS receiver only works because the satellites which emit the GPS signal account for the gravitational redshift effect of the 20,000 or so kilometers between your GPS receiver and the satellite. In fact, I think if you went ahead, you can go ahead and do the back of the envelope estimate, and you'll see that if your GPS receivers did not properly account for the gravitational redshift between the satellite and your GPS receiver, there would be errors of order several kilometers. Okay. So this is not just a measurable effect, it is an incredibly important effect for all sorts of applications. Yes?
I have a question. There was this professor, the name escapes my mind, you know, who has office near Professor Dobbs?
Yes?
And he was saying that when he just came to McGill, he was trying to organize a lab for undergrads that would measure this, but didn't work out somehow. But what is the difficulty of this experiment on an undergraduate level? Is it not possible to do it at McGill?
Well, the Pound and Rebka experiment involved using what's known as the Mossbauer effect. So the Mossbauer effect is, so you need to do very, very delicate spectroscopy, right? Because you need to measure the wavelength of emitted and received light very, very carefully. So in fact, when I took a lab as a graduate student where in fact we used the same experimental apparatus that Pound and Rebka used. Because, you know, they don't throw away whatever these radioactive, they don't throw away all the equipment. So in fact, they had just donated it to whatever student lab was. So these are, I think, things that are in principle relatively easy to do. I know that the original experiment involved essentially doing Mossbauer spectroscopy over a distance of about 20 meters or something like that. So I think that it's not something that is in principle impossible, but in practice, you're going to have to devote a rather large chunk of your physics department to doing this experiment. In particular, you need to you need to do spectroscopy over distances of 40 meters, 20 meters or something like that.
Like the building height.
The building height, yeah.
So
Why
why not?
not?
There is expensive equipment.
I think it's probably expensive. I don't think that it's in principle a very difficult experiment to do. I haven't done it. And I'm not an experimentalist, so you shouldn't listen to anything I say. But in the realm of experiments, I think it's something that is... I don't want to, I don't know of any undergraduate lab that actually does this experiment, or graduate lab for that matter. But I think it's in principle doable. Yeah. So it's not it's not a terribly difficult experiment. So let's see. So what are the implications of this? Well, light which comes from deep inside a gravitational potential will be highly redshifted. This is important in a variety of effects. So, for example, this is important in communicating with satellites, GPS, and so forth. In fact, I think the following story is sort of entertaining. The very first GPS satellite was designed, built, and launched by engineers who did not believe in relativity. So, in fact, the way that most of the GPS satellites work is that they orbit in some relatively geostationary orbit, some 20,000 kilometers away. The GPS satellites are essentially atomic clocks which emit light, which emit time signals, which tell you what time it is very accurately. And they do that by emitting radiation waves at a given frequency. That frequency is redshifted, and so you need to account for that redshift in the GPS system. And another way of saying that is the clocks on these satellites run a little bit fast, okay, because they're higher up in the orbit, farther from the Earth's gravitational potential than we are. So what they do is they have to correct the signal to take into account the fact that the clocks on these satellites are running fast. for all of the GPS satellites, these are all done in the software of the GPS satellite as it decides when to send its signal. But for the first satellite, they didn't believe in relativity, and so they didn't actually slow down the signal to account for the fact of, gravitational redshift, which is the same as gravitational time dilation. And so what they had to do then is they had to then correct the software of the GPS satellite after it was launched. They have mechanisms set up where they can do this from the ground. And so I think it's sort of interesting that, even though Pound and Rebka had observed this effect, it was not taken seriously by the people who, it was taken seriously, but it was not put forth with 100% confidence by the people who designed and built the first GPS satellite. But they eventually learned, and now all of the GPS satellites correctly take into account this gravitational time dilation factor. This is also very important in cosmology. So, as we will see, probably not next week, but the following week when we begin our discussion of cosmology, light from the early universe is highly redshifted. Essentially, when we view galaxies billions and billions of light years away, we're viewing them as if they were deep inside a gravitational potential well. Now, this gravitational potential well does not arise because there's some giant gravitational object out there, or rather it does arise because there's a giant gravitational object out there. That object is the universe, and it is the curvature of the universe rather than the curvature coming from the mass of the sun or the earth out there. But objects that we view that are very far away are essentially objects that are living deep inside a gravitational potential well with respect to us. So, light from early in the universe is also highly redshifted. And finally, one comment that I would like to make is that I have phrased the observation of gravitational redshift in this case as a test of the Schwarzschild geometry, but there's a sense in which that's a bit of a lie. Because you can also view gravitational redshift as really something whose effect just follows from the equivalence principle. So, the equivalence principle is in fact something which is deeper and a bit more basic than the Schwarzschild solution. The Schwarzschild solution depended on a general, the Schwarzschild solution depended on the equations of motion of general relativity, whereas the equivalence principle just was a consequence of the geometric formulation of the laws of gravity. And we can see quite explicitly, in fact, that the equivalence principle can be used to derive gravitational redshift, even without knowing anything about the particular geometry involved. So let's see why this is the case. The reason why this is the case is that locally, at least, gravity is, by the equivalence principle, equivalent to acceleration. And changes in velocity, namely acceleration, will lead to the Doppler effect. And the Doppler effect is nothing more and nothing less than the statement that the wavelength of light will be redshifted or blueshifted. So we could imagine doing the following experiment. Rather than putting our two physicists on the top and bottom floor of a physics department, which is the Earth's gravitational field, we could put these two physicists in an elevator, probably not in this department, given the status of the elevators, but you could put them in an elevator And you could subject them to some constant acceleration. And then you can check that there will be a gravitational redshift, a Doppler effect due to this acceleration. So let's imagine that we have a elevator which is accelerating upwards at some constant acceleration a. Now, the physics in this elevator is supposed to be identical to that in a gravitational field accelerating downwards with a strength a. So if you have these two observers in this elevator at vertical positions z1 and z2, and then if you have the observer at z1 emit a light wave with a given frequency, say at time t1, then the elevator will be going slightly faster when this light ray is received by the observer at z2. And the change in the velocity of the elevator will be a times the difference in the positions. That's just the statement that the elevator is accelerating constantly. So because the light ray is emitted at one frequency and at one velocity and received by an observer moving at a different velocity, there will be a Doppler effect proportional to delta V, so proportional to A delta Z. And if A is equal to G, the gravitational force, so remember the equivalence principle applies when you have a constant gravitational field, then this is G times delta Z, otherwise known as the difference in the gravitational potential between those 2 points. Or, for example, if you are looking in the presence of the Earth's gravitational field, this would be Gm times 1 minus R1 minus 1 minus R2. So just the equivalence principle says that there should be a gravitational redshift, which is proportional to the change in the gravitational potential. And in fact, you could go ahead and compare this to the formula that we derived above. So when R1 and R2 are large compared to R, then the gravitational field is approximately constant, provided R1 and R2 are relatively close to one another. And you could Taylor expand, and you could see that this is nothing more, nothing less than precisely the difference in the gravitational potential, at least to first order in the limit where R1 and R2 are large compared to the Schwarzschild radius. That's a nice exercise, actually, that maybe you can do in your spare time as you lull yourselves to sleep tonight with dreams of gravitational redshift. Okay, are there any questions before we conclude for the day? So we've wrapped up at this point the discussion of what I consider the core of this course in general relativity. We've understood differential geometry. We've understood the geometric formulation of the laws of gravity. We've understood the most important solutions of general relativity, Minkowski space and the Schwarzschild geometry. And we've understood the three classic tests of general relativity. So for the remainder of this course, we will be focusing on what I consider fun stuff. So we will spend approximately a week on the study of black holes, approximately a week on the study of cosmology, and about a week on the study of gravitational waves. These are the three subjects which I think are probably the three most widely studied areas of current interest in the subject of general relativity. So that is what we have to look forward to. I will see you all on Monday, unless there are any questions. Yes?
I have a question. You know that the twin example where one gets really old and one stays young?
Yes.
When the guy in the rocket is flying,
Yes.
they're kind of moving equally fast to each other. But the one who gets younger is the one who underwent acceleration.
Yes.
So with all these things that we learned, which are great, why is it that the one who accelerates gets younger, not the other way around. What is that process?
Well, there is time dilation due to acceleration. So the twin paradox really has to do with the relative velocity of one twin with respect to one another. But you could also, whenever you study the twin paradox in special relativity, you always make some approximations where you neglect the effects of acceleration. Now that you know general relativity, you could include the effect of acceleration. How would you do that? The proper time that is elapsed by one twin is the integral of ds, which is the arc length, evaluated in Minkowski space, if that's the approximation you're working in, along whatever course this rocket ship takes the twin on. So now that you know general relativity, you could completely, explicitly compute the proper time elapsed for one twin relative to the other, including all the effects of acceleration. However, I encourage you to try and show to yourself that if the rocket accelerates very quickly and then goes at constant velocity for a long time, the usual special relativistic time dilation effect is the one that gives you most of the effect. I'm not sure if that exactly answered your question. Yeah, okay, good. There was another question over here? No. Yes?
Won't the difference in velocities account for the redshift?
Absolutely. Yeah. So remember, the equivalence principle says that the following two situations are physically indistinguishable. One of them is being in an elevator which is being accelerated with constant acceleration. And the other is being in an elevator which is static but in a constant gravitational field. In both cases, you will observe a redshift. But the physics that you would ascribe to that redshift is different. The set of words that you would use is different. And in one case, you would say it's due to the Doppler effect. In the other case, you would say it's due to gravitational redshift. Now, the lesson is that those are the same thing, phrased in different language. Those are physically indistinguishable, so what matters is the outcome of experiments. And whether we call the words Doppler shift or gravitational redshift is sort of irrelevant. At the level of a constant gravitational field, those two situations are physically indistinguishable. Now, if you have a non-constant gravitational field, you need to know the actual metric, and you need to actually compute, if you want to look at the full expression for gravitational redshift. That's not something that's equivalent to the Doppler effect, except in a certain approximation. So there's a sense in which, at its most basic level, the existence of a gravitational redshift is predicted by the equivalence principle. But the detailed form, including all of the corrections when the radiuses of order r or where the difference in the radii are large, for that you really need general relativity. Okay, you'll still seem a little unhappy, but maybe, given the mob forming outside the door, maybe we can defer that until later. Okay, see you on Monday.